Hello everyone. I'm going to talk about free abelian groups today. So at some point, for some unrelated reason, I was looking at this free abelian group file. Here's the original free abelian group file in Lean. And it's free abelian groups defined as the abelianization of free groups. And I was looking at this file with Chris Hughes, and Chris Hughes said that this was a bad way to do free abelian groups. And he said life would be better if we refactored free abelian groups in terms of finsub. So I have copied this file free abelian group to free abelian group 2, and now let's change the copyright 2020, Kevin Buzzard, all rights reserved, and I'll leave Kenny as an author. There. So free abelian groups is abelianization of free groups defined using finsub. So what is finsub? I think that's probably the safest, that's probably the first thing we need to think about here. Import data.finsub. Does that work? Import data.finsub does work. Great. Oh, and the other thing is we should I should switch to a new branch. Free abelian refactor. There. So I'm importing data.finsub, and let's go to this definition. Let's see what data.finsub is. And it is the type of functions with finite support. And so this is the notation here. Great. So finsub has got finsub has been properly documented. So we're going to be looking at functions. We're going to be looking at functions with this little 0, alpha to little 0 beta. And I'll tell you what that means. Beta will always have a 0, you see. Beta is a type with a 0. So alpha is a type, beta is a type with 0. So alpha and beta are sets, if you like. And this notation here, alpha to beta, means functions from alpha to beta with only finitely many elements of alpha not being sent to 0. You see finitely supported functions from alpha to beta. There. Functions which are 0 everywhere on alpha except on a finite set, and we're going to write this as this. So this is what finsub is. So I want to completely redefine. We can probably get rid of all of this stuff right now anyway. Universe is U and V. Variables alpha type U. So this free abelian group alpha is now going to be, so what's the math? I should put an exit because I don't like all these errors. So let me talk about the mathematics. We want to define the free abelian group on a type alpha. So if we have A, B, and C are in alpha, in terms of type alpha, they are elements of the set alpha if you think set theoretically, but I now think type theoretically. So if A, B, and C are terms of type alpha, then the free abelian group on alpha will contain elements, well, terms, if you like, will contain elements of the form kind of 3a minus 2c. There, you see, and the idea is. You see, so I should say the group law will be addition, right? Group law is addition. There, and alpha is some, if you like, is a sub. If you think set theoretically, then alpha is a subset of the free abelian group on alpha. But alpha is just a set, right? Alpha is just a type, and you can't add terms together in a random type. So alpha is a subset of the free group on alpha, but so is any combination of elements of alpha that you can make using group theory. You see, using the group actions. So e.g. a plus a, whatever, a minus b, etc. 3a minus 2c, etc. So the idea is that 3a minus 2c is going to be represented as a function from alpha to z. You see, so it sends, it sends a to 3 and c to -2 and everything else to 0. There. So that's how I'm going to encode 3a minus 2c in this free abelian group. So you remember A, B, and C are terms of type alpha, but the idea is that we want to make a group that contains all the elements of alpha and all the other stuff that you need. There's no relations in alpha. A, B, and C are to be thought of as kind of independent. If you like, you can think of alpha as kind of a basis for a vector space, and then you're looking at the subgroup of the vector space generated by that basis. So this is the idea. A general element of this free abelian group is of this form. It's going to send a to 3 and c to -2 and everything else to 0. And so the definition of this free abelian group, let's move this thing down here, is going to be, it's simply going to be alpha to 0, z. There. So that's the definition. So I'm replacing, I should perhaps comment out the old definition there. So this is the idea, this is the definition of the free abelian group. And now the question is it a free abelian group automatically? Let's see. You see there was some work here. So now the question is this an additive commutative group automatically? So let's try by unfold free abelian group. And then apply, let's see if Lean knows already. You see Lean knows already. So we have a complaint. This is non-computable. Okay, so I can live with that. Non-computable instance. So there we go. So now the disadvantage of this approach is that we're not computable. And do you know what can we derive that? Let's try deriving it. Derive adcom group. There. Now you see we have a new error, and the new error is that we already have something. So now this should just be. Now you see Lean knows this already by applying this. Does this work? Oh, now it's complaining. So now the complaint is it needs a name. Foo. There. And now what happens if I take away non-computable? So now what the complaint is, yeah, okay. So Lean has figured out that this is an adcom group, and it's also made the instance. Oh, that's kind of interesting, isn't it? So what's it called? This instance will be called free abelian group, presumably free abelian group. Dot adcom group. Oh, there it was. Dot. I missed it. Yes, it's made it non-computable automatically. So now, can we prove that this free abelian group is inhabited? And so this is now a non-computable instance. The rumor is that after a while you get sick of typing non-computable, and you write non-computable theory at the top of your file. So here we go then. So we now have to make an interface for free. So we had an interface already. All this stuff down here is the interface for the old definition. And now we're going to use a new definition instead, and we're going to see if the proofs are any easier. Let's go. So what's the definition of of x? So this is the function which defines. This is the function which takes an element of x and it gives us an element of the free abelian. Sorry, takes an element of alpha and gives us an element of the free abelian group on alpha. I'm sorry, I keep speaking set theoretically. Patrick would get annoyed. So what is this function now? So this is supposed to be. This needs a doc string. The canonical function from alpha to the free abelian group on alpha. And this function, what is this function? So this should be the function, this is the function from alpha to z, sending x to 1 and everything else to 0, right? That's what that function is. And you see there's some that will have a name. So we should go back, we need to look at this, we need to look at the API for finsub. So here we are, here's the finsub. This will have a name, there will be some function. Oh, exit just, the reason, hello chat person, the reason I'm putting exit is because if I don't put exit, then I get, you see how many errors down here? I get 20 errors because I've just changed the main definition that all this file is written on. And so it just causes lots of errors. And I don't like working with files with errors. I like to have at most one. Here I have one error, right? And the error is that I haven't finished writing my definition yet. But when I find this, how to do this finsub thing, here we are, you see single AB is the finitely supported function which has value b at a and 0 otherwise. So this definition is now single, it's single x1. And it's never heard of single because I haven't opened finsub. So let's open finsub. There. And now I have a complaint about, oh, it's non-computable. So there we go. There. And you see now I have no errors, which is what I like. And so now let's go down here. So now the next thing that Kenny defined was lift. And so now, so there's his complicated, I can't even see it all. Let's move this down here. There's Kenny's definition of lift. And it uses an at, which is always a bit scary. But still, so now let's see if we can use, now let's see if we can do lift. And so this needs a doc string. If, what do we have here? You see beta, that's a lousy name. We need B, let's call it B. That's a much better name for an adcom group. F from A to B. There. So now we have, so if B is an adcom group, and a, you know, a abelian additive group, and F alpha to B is a map of sets, F lifts to a map of abelian groups. You see from here. There. So this is the yeah, this is the unit. This is the adjoint. This is the yeah, category theoretically. This is expressing the fact that free abelian group is an adjoint to the forgetful functor. The forgetful functor from abelian groups of types. There you go. There's a nice doc string. But now we have to define it. So how are we going to do this? So the idea is we need some map. We need some map, something from alpha to 0 z to b. Oh, that's not even what we need. So we need to think about this then. Firstly, I think it's worth thinking about how we're going to map, right? This is a group homomorphism. First we need a map, right? If I have, so these are thoughts, right? Let's put them in there. If I have f from alpha to b, then I want to map a natural map from alpha to z to b. There, this finitely supported functions. And now why will this exist? And this exists because B is a Z module, right? So we could certainly define this as some kind of sum, but I'm hoping that somewhere in here this will be done for us. So there's single. On finset is the so let's have a look at this. We're going to need to look at the interface for finsub. On finset is the finsub function representing f restricted to the finset s. Anyways, there's a better set representation on finset. Aha, so that's a way of making a finsub from a finset. On finset apply support on finset. So what's this map range? This is a map from aha. I don't think that's going to be of any use to us. M domain. So that's a way of extending a finitely supported function to another finitely supported function. Blah, blah, blah. That's no use to us. Zip width. I don't think this can be of any use. Yeah, this has got some function that we don't have. Erase, that's deleting a value. Sum and prod, this looks interesting. In most of this section, the domain beta is supposed to assume to be an ad monoid. So this looks like it might be useful. Prod pow relations to on finset. Now this is an ad monoid, but really I want it to be an adcom group. Blah blah blah. It's made this an ad monoid, but then the question is, why is this an adcom group? Here we are. Look, here's this sub. Oh, that's a nat sub. Here we are. Single finset sum. So now we're getting closer. Here, what's this? So this is still single. Prod neg index, neg apply, sum apply, support neg. There's the adcom group. Here's what's this sum apply. Support sum 0, sum add, sum neg, sum. I feel like have I missed it? Prod sum index, multiset sum index. What's this? Map range add monoid hom. So that's no good. That's interesting. That will that might be useful later. Right. So somehow I failed to find this, and I felt that, you see, beta was an adcom group here. So I think it was in here somewhere, and maybe we should look at a definition. Where were those definitions? Section add monoid. So here there was an add monoid. Where was the add group? this was that sub. And now here's the add com monoid, and here's the add group. It's just making this a group. So I can't immediately, what's this single sum? Maybe I should be looking for definitions. Let's have a search. Let's search around here for definitions. I see there's a whole, oh, hello. Evaluation of a function. I need something. Well, this is kind of interesting. That is a definition. Maybe I just need some. You know what, I think I might just need, do you know what, I think this might be it. This is sum. Let's look at sum. Maybe I can use sum. So there we go, there's a sum. So let's see if we can figure this out. So I'm going to define the map. So let's define lift orgs, because this isn't going to be, so let's see if I can make this definition. So I want to use sum. So this, I'm just defining the function. So now I can move this before, if I'm defining a function, instead of intros, I could move this before the colon, couldn't I? So let's take G, that's in my free abelian group. And what is this definition? The idea is that G is what? It's kind of, it's the sum, you know, it's the sum for A in A, sorry, A in alpha. It's the sum for A in alpha of what? Of G of A. You see, G is in this free abelian group on alpha, so G is really one of these finally supported functions. This is not right, though. This is not G of A, it's F of G of A is an integer. It's G of A multiplied by F of A. That's what this thing is. There. Look at this definition of sum. This is exactly what we need here, right? So it's going to be sum. And now I need a function from alpha to beta, so that is going to be G, and now this is going to be something. Here we go. And so now I have to give a map from alpha to z to beta, and that map there will be lambda a n, and now this is, I want it to be n times a, right? So the idea is n times a probably won't work, I assume. Yeah, let's try bub. Does bub work? Oh, I've got the wrong, this is f of a. Does that work? It does work. And does this work? No. Does this work? No, it doesn't. Great. So there. So that is my lift orgs. And now the question is, why is this a group homomorphism? So let's see if sum, do we prove anywhere that sum is a group homomorphism? So I'm interested in sum. We could find it, right? As you can see, there's 1,000. It's not that, it's not that. It's not that on insert sum. That's just a question about support. This is the wrong kind of sum. single multiset. So I'm looking for the statement that this is some kind of group homomorphism. Single sum apply. I don't think we have that. Support sum, yeah. Here we go. What's this sum add? This looks good, doesn't it? So sum add. Ah, yeah, this is exactly what we've got because the integers are an adcom monoid. So sum add is what we need. Sum neg sum sub. I see. So maybe we should just go for this. Let's go for this. I'm going to make an abelian group homomorphism. So I'm supposed to define this. So this 2fun will be this thing here. I'm tempted to ditch some orgs. That thing there. That hasn't gone well, has it? Oh, because it's lambda g. There, that's gone okay. And now let's sorry this. And now this map add, we just found this. What was this called? This is called sum add. Let's see if sum add does it for us. Let's just have a little glance around, see if there's any more useful. Prod sum index, multiset sum index. This is about sums of sums, I think. Map domain. I don't think I want that. Map domain needs map domain comp, map domain sum. No. Co-map domain. I don't think that's got anything to do with what we're doing. Doesn't look like anything to do with what we're doing. I'm just looking at everything with a sum in. You see, I'm searching for sums, and I can see on the right these orange dots. Subtype. Yeah. Multiset, I don't care about that, I don't think. To multiset map, count to multiset. Curry and uncurry, I don't care about that. What's this? Sum. Oh, this looks interesting. Yeah, I don't know though. Sigma sum. I think we need that. And here's the last one down here. Sum idlative lit. So there was this stuff here. Not the carrying stuff. Before the carrying stuff, what was this? Oh, maybe this is irrelevant. Okay, let's go for it. It was called, what was it called? Oh, great, I've now forgotten what it was called. Oh, is my cursor still there? Single sum, sum apply, support sum, oh, sum zero, that's interesting. Sum zero and sum add. So let's try using sum zero and sum add. We could try sum zero here. Let's try sum zero. How close are we to proving that? Oh, that's compiled, I think. Oh no, there's still an error with lift. Oh, it's complaining that lift is non-computable. So let's make it non-computable. Oh, sum zero has worked. So let's try sum add. Oh, it doesn't like that. Okay, let's try improving this. So this says lambda x and y. Actually, x and y are quite good names for elements of a group, aren't they? Why don't we go with let's go with x. I like x. And now what? Lambda xy sum add. What's the error? This is expected to have blah blah blah. Oh, it looks like this goal here says that the sum of something add something equals the sum of, this looks the other way around. This looks like it says blah equals blah add blah, and I'm supposed to be proving, oh no, I'm supposed to be proving that blah equals blah add blah. So it's a shame that this isn't, it's a shame that this isn't right. So what does this want? This wants, oh well. So maybe it's not what we want at all. Okay, so let's try and fill this in. It wants F and H. Oh, you see, it's maybe not. Let's try converting it. Let's try this. Convert sum as. Let's see how close we are. And now I have 3 goals. You see, these goals don't look great, do they? And now I have 9 goals. Do these goals look good? Let's try using 2. Let's try and get the right number. These goals don't look right. So let's go back to, let's try 0. What does that do? 10 goals. Let's try 1. Type. So it cannot, okay, let's give it a hint. So let's convert sum add. What is this sum add? We want alpha, beta, gamma, blah, blah. So I think the first 5 we can skip. I see, this is somehow, we want to sum f's. This is the wrong lever, isn't it? This is the wrong kind of sum add. We would like to add, this is adding h's. This is the problem. We have a fixed f and we're adding h's. But in our application we have 2 different f's. We want to add them. So where was the proof? Where was the proof that this was an abelian group? Excuse me. Where was the proof that this was an abelian group? Because let's look at add group. There. So how does it define? So how does it define addition? It defines addition using plus. So what is the definition of plus? We need a has_add. Here it is. So it uses zip width. Huh. How many zip widths are there? Oops. Declarations about zip width. Do we really want to use zip width? Zip width apply, support zip width, and that's it. No zip width add. Okay, so we're supposed to be using addition. Well, maybe we should have a look and see what we're actually supposed to be proving here. What does this say? So let's try refl. No. Let's try sim. No. So this is really annoying. Let's try congra. Nope. So how are we going to define this? So we have to prove this theorem. Let's try this rewrite sumadd won't work, right? So somehow sumadd was somehow hopeless. So I really hope I don't have to prove this. Is there more FinSup stuff? Let's have a look. What's this pointwise? Pointwise product on FinSup. So beta is a semi-ring, then this is a semi-group. That's great. So that's not it. What's in lattice? Lattice structure on FinSup. So here everything is a partial order, so that probably won't be of any use to us. So I guess the other place to look is big operators, right? Where's that in algebra? What's in big operators nowadays? Order, pi, ring. Let's have a look in here. Is there anything about? Let's see if there's any. Let's see if there's any FinSup stuff in here. What's my goal here? Why don't I have a look for this? In here. Nothing about FinSup in here. This is a blow. Let's try basic. Nothing about FinSup in there either. Oh, well, unfortunately, this might mean that we have to prove it. So how are we going to do this? Oh, this is really annoying. I would finish work. I don't think finish or tidy have got a chance. I'll try them. Finish does not work. Tidy. Chain made no progress. So I might have to prove this by induction on Y. Because there's certainly an induction principle for finally supported functions. Oh, how annoying. Let's go back to data.finsub. There. Add. That's the only time that add is used. Oh, do you know what? This could be a prod. There could be a prod lemma, couldn't there? You see, we've got this. Prodcom, prod ITEC, prod pow. We've only got what? The problem is we've only got one F. This is the problem. I want to have some theorem about two. Oh, here we go. Add apply. Support add. Support add. So this is looking much. This area is looking much better now. Single add. Oh, but we've finished. Okay. So how was this done? So how was add a sock proved here? They took them apart. So let's try taking them apart. So instead of lambda xy, let's do this. Get in here. And now let's try rintro. Rintro I don't know what things are, so let's have A, B, C, comma. You see, they've really taken it apart, haven't they? So it's S, F, H, F, there, and then T, G, H, G. And so now we have to prove that some sum equals some sum. We could probably de-simplify this, can we? No, hard luck. So I'm looking at the proof that addition's associative, and it uses X now. Aha. But I don't think we can use X because we need to understand this sum. And what kind of sum is this? This is this sum, which is finsup.sum. So I need to know how to, if I'm going to write this proof myself, I need to learn how to control finsup.sum. So dsimp finsup.prod. So let's try dsimp finsup.sum. Dsub finsup.sum. Has that done anything? It's done something, maybe. I might have to actually think about what we're doing here, rather than just blundering through hoping it's all going to be easy. We now need some statement about what kind of sum is this now? This is now a finset.sum. So maybe apply finset.sum add. Is that a thing? Finset.sum add distrib. Let's try that. That looks interesting, doesn't it? Does that do? No, hard luck. It's kind of annoying that dsimp won't change this to s.support.sum. This seems to be, we seem to have an add. This where is the object I'm looking for? This object here, where does what closes that bracket? Where does this bracket get closed? Here we are. This object here is x add y. So this says x add y Bob. So we could maybe rewrite add small. That's kind of annoying. Oh, is it under the blooming lambda? Simp rewrite add small. That has worked. Does simp do this yet? It would be great if simp solved it. Simp does not solve it yet. So simp rewrite add small. And now we have sum. And now this is the sum of A add B. So can we rewrite? Simp rewrite probably takes it like this. Can we now do sum add? Is that a thing? It doesn't like sum add. But that looks perfect. Why won't it let me do sum add? This says sum of, what kind of sum is that? That's a thinset.sum. So why can't I do rewrite thinset.sum add? That should work. Oh, it doesn't work because it's not there. Thinset.sum add district, let's try. I was a twit trying to apply it. I was going to rewrite it. So now how are we doing? Whatever does this monster say? This is, I see, This sum here of that, add this sum here of that equals this sum over a slightly different This is now close, isn't it? Is this, what happens if I do congra now? Now I've got to prove, it's gone too far. Congra 1, let's try that. This now says, we add these two functions, we add f and g, oh, this is not true. What? This says f add g, oh I see, cursors, it's not true. The right hand side just has an f and the left hand side has an f add g. So I'm making a real hash of this. So the left hand side is a sum of, what does the left hand side say? It's the sum of, there's some crazy f1 there. What's that f1? What is this object? It's f1x, obviously. Oh, it must be some implicit thing in the sum. I think this says the sum of x times f of x add the sum over what? And this is now x times g of x equals the sum of I can't tell what these equals the sum. Oh, so maybe this is fine. Let's go back to that. Let's go back to that congra primed 1. Let's have a look at this first goal. So this is a sum over a large support. This says that the sum over some, this says that a sum of some function equals the sum over some other set of some function. And so those sums are going to be equal because I'm going to be able to prove that this sum vanishes. This is interesting. I need the sum theory. Yeah. this would be easy if I had the sum theory, if I'd actually PR'd the sum theory which I need for MATLib. Okay, I think that this goal says that the sum of x times f of x over a certain finite set containing the support of f equals the sum of x times f of x over some other finite support containing f. So this is some lemma about sums, about fin set sums. So let's take a look at, I want some lemma that says the sum over two fin sets is the same. I want that the sum over two fin sets is the same if, where do we start? Where's the definition of sum? So what's sum in lim? Oh, that's just direct sum of two things. That's no good. You see, there's an interesting thing. The sum of f. Yeah, there's a minor change of what we're summing. We're summing over two finite sets. We're summing a function over two finite sets. And my claim is that this is that the two finite sets aren't necessarily equal, but the sum is zero. The sum is zero if we're not actually in the other finite set. So what's this? So this is the very beginning. So that's some functoriality of sum. This is the beginning. S dot filter P. I think those are just the same, aren't they? What's this? Function embedding subtype prod congra. What does prod congra say? Prod congra says that the things have to be, S1 has to equal S2. So that's exactly the problem. So we could use that. And now this is like an inductive property. Oh, do you know what? Maybe we could use this. Oh, maybe not. A telescoping sum, a sum of a fin set of size 1. If a function applies to point is 0, the sum is unchanged. Yes, yes, yes. Yes, yes, yes. That's no use. Huh. Oh, this is extremely frustrating. So I'm stuck. I mean, I'm not stuck, but it will take a lot more than 2 minutes to define this addition. So we've done very poorly. Oh well, rotten luck. We've done very poorly at defining what is going on here. Lift F. What did you used to say? Was lift? Yeah, lift was an abelian group polymorphism. So, oh, I see. This is all just. Oh, how annoying. So maybe I should have done. So I should have maybe used lift orgs. And then I should have, I mean, lemma map 0. My alarm is going off to tell me to do something. Oh yes, I'll do that in 5 minutes. Maybe I should do some revision and then learn how to do this and come back next time. When? Thursday. Okay, so there's my strategy. So sorry for being so slow. But I need to figure out how to do addition. Thanks for watching.